I share my screen. So we see in the test benches for the combinational circuits like half adder, full adder, and multiplexer. Okay, 2x1 multiplexer, encoder. So all those things mainly explained in the data flow modeling. Okay. Suppose 2x1 mux also we already see. Okay. Today we'll see the 2x1 mux using behavioral modeling. Okay. So 2x1 mux using and 2x1 mux and 4x1 mux using behavioral modeling. Okay. Um, so first we'll see the 2x1 mux. Okay. So 2x1 mux how to write first module module, and it will start with I told you the valid identifiers and invalid identifiers. Okay, so invalid identifiers means when you are writing your module name with number, the compiler will not take. Okay, so if it is underscore means it will take. Okay, so underscore 2x1 mux. Okay, so what are the input for the mux? Input input s. Okay, and input. Okay, input I am using the vector concept, that is vector 1 down to 0 inp. Okay, and next output if you are using behavioral modeling, output should be rich data type. Okay, port rule connections I told you. Okay, always at the rate star. Okay, so this is the implication operator, or you can use always at the rate inp comma s also. Okay, so that means these are the sensitivity list. If there any change in the inputs, then there is a change in the outputs. Okay, that you need to declare in the sensitivity list. Okay, always at the rate like that. And if it is multiple statements are there, you need to write between the begin and end block. Okay, so begin I am using if else statement. Okay, so that is if else statement. Okay, so so that means if s equal to 1. Okay, y equal to what? Inp of 0. Inp of 0. Okay, else y equal to inp of 1. Okay, I am using if else statement, end and end module. So last class we seen the data flow modeling. There I used assignment statement, continuous assignment statement, assign, and I am using the ternary operator. No, okay, I use the ternary operator. Okay, so that means whatever the code we are writing. Okay, we are writing the code in three blocks. What are those blocks? One is assign block. Assign blocks means I need, so when I use data flow modeling, I need to use the assign block. Okay, and if I am using behavioral modeling, I need to write your code. You need to write your code in always block. Okay, so always block. This is behavioral modeling. Okay, so BHM behavioral modeling, and initial also. Okay, initial block. So these two are synthesizable. These two are synthesizable. Synthesizable means what? You have synthesizable constructs and non-synthesizable constructs. So that means whatever your code is there, that will be converted into gate level netlist. That is into hardware. Okay, gate level netlist. Gate level netlist. Okay. Initial block is non-synthesizable. So by using this initial block, we can not convert your code into hardware. Okay. So not converted to hardware. Not converted to hardware. Okay, so where you are using initial block? So you are using the initial block in the test benches. So by using test benches, you can see the simulation only. So no need to make the hardware by using test bench. So that's why we are using the initial block in the test bench. Okay, so these two are nothing but we call as procedural assignments. Okay, procedural assignments. Okay. So this is about the 2 cross 1 mux by using if else statement. Is it fine? Do you understood? Any doubts or queries? Shall I move forward? So 2 cross 1 mux means here we already discussed in the digital. You have two inputs, so that is INP0 and INP1 and one selection line and one output. Okay, so when selection line is equal to 0, INP0 is connected to the output. Okay, when selection line is 1, INP1 is connected to the output. Okay, at a time any one of the input is connected to the output. Okay, this is 2 cross 1 mode. Is it fine? Shall I move forward? Hello? Yes? No? Any doubts?
Yes, sir. Move on.
Okay, yeah. One second. Maybe to the last slide. So in order to write the code, you need to be strong in the digital. Okay. So all the combinational and sequential circuits you need to be strong. Then only you can write the Verilog code. You need to understand the operation of digital. Okay. And next 2 cross 1 must uh, using case statement. Okay. So first last class in the during the behavioral modeling, I told you in the behavioral modeling you have procedural assignments and you have procedural statements. Procedural statements. What are the procedural statements? Like in C, you already studied, no? Like if else statement and and you have case statement, okay, and for loop, okay, while loop, and repeat, and forever. These all are nothing but procedural statements. Okay. So here I am writing the 2 cross 1 marks by using case statement. So module as 2 cross 1 marks. This is my module name or identifier. I need to declare input yes, and input 1 down to 0 INP, 1 down to 0 INP, and output I am declaring output reg y, output reg y, and I'm using always block, always at the rate star. Okay, begin. If it is a multiple statement, you need to write between the begin and end. Case, case yes, case yes. If it is like one tick binary 0, one tick binary 0, y equal to what? INP of 0. Okay, and if it is one tick binary 1, y equal to INP of 1, INP of 1, INP of 1. And for the case statement, you have a default statement. Okay, default statement. Why it is default statement, I will explain. Okay, in order to avoid the latching, if you are not declaring this default statement, it will infer as a latch. Okay, so default y equal to one tick binary x. Okay, default values don't care. And next end case, end and end module. Is it fine? Do you understood this code by using case statement?
Yes, sir.
Yeah. Okay. Next test bench. Okay. So test bench for both if else statement and case statements are same only. In the instantiation, you need to change the design name. Okay, that is the only difference. Okay, test bench for 2 cross 1 marks. Last class I told you only 4 steps are there. Can anyone unmute yourself and tell me what are the 4 steps? Waiting for your response. Yeah, tell me the steps for the test bench. I'm expecting something from you, but you're not. Yeah, okay, I will tell you. So module My test bench name is 2 cross 1 mux underscore tb. Okay, you are not declaring the inputs and outputs, only this bracket. Okay, what is step 1? You need to declare the internal variables. Okay, so declare the internal variables. Okay, internal variables. Here you need to follow the port rule connections. So that means whatever this in that means that you are giving the stimulus, no, that stimulus that you need to declare with reg variable. Okay, so inp 120 inp comma yes, and next so whatever the output that you need to declare with wire data type. Okay, and these are declaring the internal variables. And step 2, you need to instantiate the design. Okay, you need to instantiate the design. Okay, instantiate the design. Okay, whatever the design name is there, you need to instantiate. So in the test bench, so what is my design name? Ash underscore 2 cross 1 mux. Okay, and let us take my instance name is dut, design under test. And what are, so I am using connection by position with order list. So I need to declare inp0 and inp1, and next selection line yes, y. Okay, so this is instantiation connection by name with order list. Connection name by name with order list. Okay, is it fine? Second step. Okay, step 3. What is step 3? Initialize the reg variables. Okay, initialize the reg variables. Initialize the reg variable. Here you see begin initial begin. What are the reg variables? Inp of 0 comma inp of 1 comma yes, by using concatenation operator. Okay, equal to 0 and end. Okay, so till here is it fine? Do you understood how I am doing? Shall I move forward? Yes, no? Okay, next you see step 4. What you need to do? So driving the inputs to the design. You need to driving the inputs to the design. Inputs to the design. Okay, so how to drive the inputs to the design? Within an initial begin and block, initial begin. Okay, initial begin, I am giving is equal to 0, and inp of 0 equal to 1, and inp of 1 equal to 0. Okay, so s equal to 0 means which one is connected? Inp 0 is connected. First case, s equal to, so you have inp 0 and inp1, no? So inp0 inp1 means which is connected? So this is connected. Okay, so inp0 is 1 means you are getting y equal to 1. Okay, after I am giving a delay after 10 minutes, I am giving s equal to 1, inp of 0 equal to 0, and inp of 1 that is equal to 1, and end module. So in the second case, what I am doing, dollar finish also you can use. Dollar finish means you need to, this is a system task, you need to end the simulation. Okay. So second case, you are using inp0 and inp1, inp0 and inp1, and output is y. Okay. So when selection line, so here this selection line is 0, and this is selection line is 1. So which is connected? INP1 is connected. What is INP1? 1. So why you are getting 1? Why you are getting 1? Is it fine? Do you understood the test bench and design? Shall I move forward?
Yes, sir.
Yeah. Yesterday we are doing the some codes there itself. I will do. Okay. See here. Just to correlate with the operation of 2 cross 1 marks. Okay. Mm, it will open. Okay. See here. This is the code related to 2 cross 1 marks by using if else statement. Okay. So here same thing whatever I explained. Okay. If selection equal to 0, y equal to a, selection equal to. So like this also you can declare means without vector also you need to declare two inputs, input wire a, input wire b, or input wire selection, output reg y. Like this also you can declare. Okay. And this is the 2 cross 1 mux by using case statement. Okay. uh, so here if you see this code, module mux 2 cross 1 case, input wire a, input wire b, input wire selection, input you are declaring with y data type and output you are declaring with red data type, always at the rate star begin case select. So one tick binary 0, y equal to a, one tick binary 1, y equal to b. What is the default statement? Y equal to one tick binary x, end case, end and end module. Okay. And here you can execute this in Quasta sim also. For the Quasta sim, what you need to do means you need to create a separate folder for design and test bench. Okay, I created three folders: RTL, TB, and sim. Okay, mostly you try in the Vivado only. So here you see these are the codes. This I am using GVim. Okay, TB 2 cross 1 if else statement. Okay, so I can use for loop also. Okay, for loop means I can see each and every cases. Okay, so module TB mux 2 cross 1 if first you need to declare the range variables and that instantiation. This is instantiation. So this is nothing but connection by name. Okay, I am using connection by name. Whatever you want you can use, but in the most of the industry they are using connection by name only. Why? Because like if you have so many inputs, suppose 250 inputs or 500 inputs are there. So if we are using connection by position means any signal is missing means you will get a bug. So connection by name means like vertically you need to see. Okay, like this you need to write. Okay. So this whatever the output inputs, whatever the variables outside the bracket are design inputs and outputs. Variable inside the bracket are nothing but test bench variables. And declaring an integer data type integer I. Initial begin dollar display. So this is selection A B Y. Dollar display. Okay. I'm displaying this. So taking for how many inputs are there? Three inputs are there. So how many combinations I need to check? Eight combinations I need to check. Okay. So for this I am using for loop. Okay. Select comma A comma B. Okay, equal to I and hash 10 dollar display and displaying this value and dollar finish and enter. Okay. So this is the test bench for 2 cross 1 marks and this is the test bench for case statement. So test bench for both are same only. Where you will get the difference means this instantiation you will get the difference. Remaining all are same only. Okay. Remaining all this is 4 cross 1 marks. Sorry. 2 cross 1 marks case statement. TB. So this is 2 cross 1 mux, 2 case statement. Okay. So here only instantiation will change. Remaining all are same only. So by using for loop also you can give the test cases. You can give the stimulus. Okay. Shall I execute this code? The Vivado? Give response. Shall I
Yes,
execute
sir.
this code? Yeah. So first if else statement I am using. Okay. So first what I need to do? So just module is there, no? So this module you copy this, go to Vivado. So in the design sources you need to add the design source. Okay. So you need to add the design source, create file. Okay. File name is must 2 cross 1 f4 and choose the location. Choose the location. Okay, this is my location. You can use combinational circuits also. So you choose this location. Select OK. Finish. That code will be stored in that your project. Okay. So mux 2 cross 1 if is created. Okay. So go to this GVim. Select all. Copy and paste here. Paste here and save this file. End module. Yeah, end module. So you are using if else, no? Set as top module and go to the test bench. This is the test bench. Okay. So select this test bench file. Just copy this and go to Vivado. Go to the simulation. Select simulation. Add the simulation source. Create simulation source. Create and copy this simulation file. Choose the location. I'm using combinational circuit. Okay. Finish. Okay. Yes. So my simulation source is created. Okay. See here. Where is my simulation source? This is TB 2 cross 1 mark. Go to this code if statement. Select all. Copy and paste here. Save this file. Now it is saved. Okay. I need to see the simulation. No. Set as top module. Okay. Set as top module. For every design, you need to see the elaborated design also. Okay. So my design is first top module. No. So open elaborated design. Just it will take time. Yeah. You got 2 cross 1 marks. No. I naught and I1 and selection line and output is Y. A, B are the inputs and selection line. Okay. So this is the elaborated design. And next I need to see the simulation. Run simulation, run behavioral simulation. So I think in the TCL console also you can see the output. See here. When selection line equal to 0, which one is connected? Whatever the A value is there, that is connected to the output. Okay. When selection line equal to 1, whatever the B value is there, that is connected to the output. Okay, you can see the output in the TCL console, or you can see in the waveforms also. Just expand this fit to page, and next this is a for low, this is not required. See here, when selection line equal to 0, a equal to 0, b equal to 0, y equal to 0. Okay, when selection line equal to 0, uh, so whatever the a value is there, a is 0, no, you are getting that. Okay, so when selection line equal to 0, a equal to 1, no, you are getting this value. Okay, a equal to 1, and I'm checking each and every possible cases. Okay, three inputs are there, no, so that means 0 0 0 1 1 0 1 1 for selection line equal to 0, 0 0 0 1 1 0 1 1 for selection line equal to 1. Okay, and 1 1, so that is input is 1 1, selection line equal to 0, I am getting the output, a is connected to the output. Okay, similarly when selection, I am making selection line equal to 1, now b is connected to the output, so b is 0, output is 0, and now 0 1, b is 1, output is 1, and similarly like b is 0, output is 0, and b is 1, output is 1. So can you observe the waveforms and output in the TCL console? Can you able to observe? Can you able to observe the output? Is it fine? Just to give response so that I will move forward. Any doubts or queries? Okay. So if it is case statement means, open this case statement. Okay. So just copy this and create the design source. Next, create the file, case statement, create the folder, select OK, finish, OK, yes. So file name and the module name can be same only, nothing will happen. So I created this case statement. So go to this case statement, select all, copy, and here, paste here, case statement, select all, copy, and here paste here, case statement. Okay, save this file. Set as top module, and go to simulation. So test bench using case statement. Okay, this is my module name. This is my module name. Copy this and create the simulation source. Add the simulation source. Create. Okay, make sure that when you are adding the design and simulation source, you need to create. See here, when you are adding the design source, you need to add or create the design source. Okay, when you are adding the simulation source, you need to add or create the simulation source. So now I am creating the test bench, no? So you need to add the simulation source. Okay. So Verilog and my simulation test bench, my module name, test bench module name is TB underscore mux underscore 2 class 1, and choose the location, select OK, finish. Module name is also same, yes. Okay, and my TB underscore case is created. Okay, so set as top module, and this code is there, no? TB underscore case, select all, copy, and paste here, paste here, save this code. So if you want to elaborate the design for 2 cross 1 mux by using if else and case statement, you will get the same circuit only, but you will get the difference in the 4 cross 1 mux, that I will tell you. Okay, open elaborated design. So you got the design. Okay. So this is my schematic for 2 cross 1 max using case statement. Okay. So close this and run the simulation, run behavioral simulation. So you'll get the same outputs only. So you can see the output in TCL console also. See here. So when selection line equal to 0, whatever the value of A is there, that is assigned to Y. When selection line equal to 1, whatever the B input is there, that is assigned to Y. Okay. So this is the simulation, and you can see the waveforms also. Same thing you'll get. Okay. So expand this bit to page. So selection line equal to 0, A value will become to output. Selection line equal to 1, B value will become to output. You can see in the simulation only. Okay. Is this fine? Do you understood the 2 cross 1 mux by using behavioral modeling? Shall I move forward? Any doubts or queries? Hello.
No queries, sir.
Okay. Yeah. Oh, yeah. Yeah. Next, we'll see the 4 cross 1 mux. Okay. So 4 cross 1 mux means here RTL separate folder. 4 cross 1 mux using case statement and if else statement. See here. This is if else statement. Okay. So like excuse me. So module 4 cross 1 mux if so input wide I'm declaring with a vector. Okay, 3 down to 0. 3 down to 0 means how many inputs? 4 inputs. Okay, D. So those inputs are D0 to D3. D0, D1, D2, D3. And input wire 1 down to 0. How many selection lines are there? 2 selection lines are there. So selection line 1 and selection line 0. So output I need to declare with reg y. Okay. So declaration of input and output always at the rate star begin. Okay. Star means what? It will be applicable for all inputs and outputs. If there any change in the input, then there is a change in the output. I am using if else statement. If selection equal to 2 tick binary 0 0, y equal to d0. Else if selection equal to 2 tick binary 0 1, y equal to d of 1. Else if selection equal to 2 tick binary 10, y equal to 2. Else y equal to d3, end and end module. Okay. So same thing like depending on the selection line, any one of the input is connected to the output. Okay. So just we will observe the circuit. There will be difference when you use the if else and case statement. And coming to the test bench, I'll tell you the case statement also. Here 4 cross 1 case statement. Okay. So we'll run in the Vivado and I will show you. So here you see module mux 4 cross 1 underscore case and declaring the inputs for that is 4 inputs, 2 outputs, and output is reg data type y, always at the star case select 2 tick binary 0 0, y equal to d0, 2 tick binary 0 1, y equal to d1, 2 tick binary 10, y equal to d2, 2 tick binary 11, y equal to d3. Default is what? Y equal to 1 tick binary x. Okay. So for case statement, you should have the default statement. You need to end the case, end. You need to end the begin and end module. Okay. This is using case statement. And coming to the test bench, TB. So here TB equal statement. Okay. The steps are same only. The instantiation value name will change. Okay. So module TB mux 4 cross 1 if. So I need to declare the internal variables. Okay, D and the selection line with reg variable. So these D inputs are 4 and text bench variables. Selection lines are 4 and output is declared with y data type. I need to instantiate that design in this. Okay. So mux 4 plus 1 if UUT. Whatever the variables outside the bracket are nothing but design inputs and outputs. variables are inside the bracket are nothing but test bench variables. I need to declare integer I, okay, and initial begin. I am displaying this, okay. So how many inputs and outputs are there? Total you have four inputs and two outputs. 2 power 6. 2 power 6 means I need to check for 64 combinations. Okay. So 64 combinations I need to check. So for this I am using for loop I equal to 0, I less than 64, I equal to I plus 1 begin, and concatenation operator select comma d equal to I. Every 10 time minutes I am giving dollar display. This I am displaying end and dollar finish and end module. Okay. And test bench by using this case statement also. See here. So methods steps are same only. This just this one will change. Only this instantiation name will change. Okay. Remaining steps are same only. Okay. That is same as if else only. Okay. So first go to the design source, add the design source. Next, I need to create the design source. No, first I am doing with if else statement. I means editor mode. Okay. In GVim, I means editor mode. Escape means command mode will get. Okay. Just study about GVim commands. Create and choose the file location, combinational circuit, okay, finish, okay, yes. My 4 cross 1 mux is created. Okay, this one is my 4 cross 1 mux. Okay, set a stop module, and by using if else statement, select all, copy, and here paste, save this file, and test bench also. So create the simulation source, add the simulation source. Okay. So what is my simulation file? This is my simulation file. tbmux if, tbmux if. Okay. Just copy this and create and choose the location where you want to save the file. Select OK, finish, OK, yes. Now tb if, select all, copy, and tbmux now, tbmux if. Okay. So right click, set as stop module, and save this file. Save. One second. It is closed off. Hey, Gidore, Sanu, Gidore. The simulation sources. Okay. The simulation sources, TB, I need to create no. TB underscore mux and module. I'm getting the, one second. TB underscore if else statement. Select all, copy, and paste here. One second. This is TB, no? Yeah, this is TB. Which one? Mm, TB 4 cross 1 mark. TB 4 cross 1 mark. Or otherwise, simulation sources I created. TB. So create the simulation source. Otherwise, I will create one project. It will be clumsy. Project is uh, multiplexers. Okay, multiplexers, multiplexers, and RTL codes. Save folder. Next. Create. What is my file name? Uh, so so by using 2 cross 1 mux if else statement, copy this and say okay. Next. Product name is multiplexers. Yeah, here file multiplexers if else. Next. Finish. Yes. Save. Okay. Yes. So module wise you can create the project. Okay, or it will be easy. Go to if else statement. If else statement. Select all. Copy. Copy. And paste. Save this file. And go to simulation sources. Add simulation sources. Create simulation sources. Testbench is this one. Copy. And here create the testbench file. Okay, my testbench file is also saved. And next, my testbench file is created. Open this and so select all if else statement. Testbench by using if else statement. Copy. So paste. Save. End module. Save. Yeah. Now, if you want to see the design, open elaborated design. By using if else statement, I am checking the design, how the design will look like. Okay. See here, you are getting like a priority marks. Okay. So if this one is the means if s equal to 0, y equal to 1, and if s equal to 0 0, y equal to 1. If s equal to 0 1, y equal to so second input will be connected. 1 0 means third input will be connected. 1 1 means fourth input will be connected. You are getting like a priority multiplexer. This is nothing but priority multiplexer. And next I want to see the simulation, run behavioral simulation. So, so just open this fit to page. So I can see all the possible combinations. Okay, just I will zoom this. I can see some possible combinations. So see here. Uh, so this is in terms of binary. You can go to radix and binary. Okay, it will show binary. Go to radix and set on binary, it will show binary. Okay. So if it is 0 0, what is connected? Selection line is 0 0 only. Okay. So here y is connected to, here y is connected to 0. Okay. And here y is connected to 1. Y is connected to 0. Y is connected to 1. Okay. So only this D0 is connected. Whatever the D0 pin is there, that is connected. Why? Because selection line is 0 0 only. No. So this is Y0. D0 is connected. Okay. Here D0 is 1. That is connected to the output. Okay. Like this. You can analyze. Okay. Suppose if selection line is 0 1. See here. If selection line is 0 1, which is connected, this D1 is connected. Okay. See here. D1 is connected. D1 is connected to the output. D1 is 0 only. Here D1 is 1. So output is, that is connected. And D1 is 0. Output is 0 only. And D1 is 1. The output is 1. D1 is 1. Output is. Hope you understood. I can see each and I can see all the possible combinations. Okay. 1 0 means D2 is connected. Okay. D2 is connected to the output. Here D2 is 0 only. So again, here this one is connected like this. Okay. So this is I can see. One second. Discard. I will discard this. Okay. So this is how to find out in the if else statement. Okay. By using a case statement. So just so copy this module name. Go to design sources. Add the design source. Next, create the design source. Check the location. I'm using multiplexers. Okay. RTL coding multiplexers only. Okay. Finish. Okay. Yes. So using case statement, select all, copy, and next paste here. Run this code. Okay. Save this code. Save this code and go to simulation source. Create the simulation source. Create the source. What is my TB underscore? That is this name. Okay. This one. Just copy here and paste here. Choose the location. Select. Okay. Finish. Okay. Yes. My testbench file is created. TB testbench file is created, and this is TB file. Select all, copy, and here you paste this file. Run this. Save this code. Save this code, and you need to make a set as stop module. Set as stop module, and the simulation by using testbench also you need to make a set as stop module. After this, I want to elaborate the design. Okay, I will see the changes. Open elaborated design. Open elaborated design. So you are getting normal marks only. Previously, by using if else statement, you got what you got by using priority multiplexer. No, you got priority multiplexer. But using case statement, you will get normal multiplexer. Okay, normal multiplexer diagram you will get. Okay, so this is one of the interview question. When you write the code by using if else statement and by using case statement, when you elaborate the design, how the compiler will make your code into schematic means by using if else statement you are getting priority marks, and by using case statement normal operation, normal thing you will get. Okay. And run the simulation, run behavior simulation. So you are getting the outputs, different output cases in the TCL console, and you can see in the waveform also same simulation outputs you will get. You can zoom this, and you can see for each and every combination. Okay. So right click if you want to see in the binary. In the radix, go to radix and binary is there. Okay. In the selection line also, go to radix and binary. Okay. So 0 0 means this I0 D0 is connected to the output, and 0 1 means D1 is connected to the output, and D2 means same thing, D2 is connected, and 1 0 means D3 is connected. So this is how you need to do the code for the multiplexer. Do you understood? Shall I move forward? Hello. Yes. No. Doubt.
Yes, sir.
Yeah. Yeah. Thank you. So next, so I will tell you how like latch is means why you are using latch as a in default multiplexer. Okay, or default in case statement. Okay. Suppose if you take one code, suppose always at the rate I am using the selection line A R B R selection. Okay, begin begin begin. I'm using case select case select and begin. Okay, case select um, begin begin. One tick binary 0, that is equal to what I'm using out 1, that is equal to A. Okay, and out 2 equal to I'm initializing to A only. Okay, I'm initializing to A only. And if it is one tick binary 1, okay, I'm initializing, that is out 1 equal to so I'm initializing the out 1 and out 2. Out 1 equal to B. Okay, out 1 equal to B. End case and end module. Okay, so now can you anyone tell me what is the output of this code? You have two inputs, A and B, and one selection line. Okay, now what is the output of this out 1 and out 2? What is out 1? I am using 2 cross 1 now. So normally here when that means out 2 I am not using. So that means when selection line equal to 0, which is connected, so that means A is connected to out 1. A is connected to out 1. Okay. So when selection line equal to what? When selection line equal to 1, anyway B is connected to out 1. Okay. B is connected to out 1. Okay. So this is simple only. One more code I will write. Suppose here always at the rate A R B R selection. Okay. Begin case statement. I am using case statement only. Case select begin begin. If it is 0, out 1 equal to A. Okay. Out 2 equal to A. Out 2 equal to A. Okay. End end end. Okay. And next 1 begin out 1 equal to B. Out 1 equal to B. End case end. Okay. Again end module. Okay. So here what happens? So that means so for first marks two inputs are connected. Okay, what are those inputs? A and B. Okay, so this is out one, out one. Okay, again out two is there. Okay, one more out two is there. That means depending on this logic, when when selection line, that is selection line equal to 0 means out one is connected to A. Okay, when selection line equal to 1 means 1 means out one is connected to B. Okay, so here again uh, again one more 2 cross 1 mux, this is nothing but B. Okay, so that means here let us take out to 2 out yeah out one is B. Okay, uh, yeah, so here I'm using one more, that is out to, out to. Okay, here one more thing is there, that is out to, that is equal to B, out to equal to B. Okay, so here out so for one I used this one. Okay, here out to 2 I'm not using. Okay, here I'm not using, so that means this 0 pin I'm not using. Okay, so how it will take, tool is going to form a latch, tool is going to form a latch. Okay, in order to avoid that inferring as a latch, latch means what? It will take the previous state only. Okay, we already seen the latch now, so that means output will be like selection line is there. When selection line equal to 0, so that means it will select the previous value, whatever the previous value is there, that it will be selected. When selection line equal to 1, our B is connected to the output. Okay, so in order to avoid this, we are using the default statement in the case statement, default statement. Okay, why you are default, why you are using default statement? This will avoid the formation of latch, this will avoid the formation of latch. In order to avoid the formation of latch, we need to use the default statement in the case statement. Okay, so this is also one important interview question. Why you are using default statement in the case statement means, in order to avoid the formation of latch, we are using the default statement. Is it fine? Do you understood? Shall I move forward? Hello. Next is I'll tell you ripple carry adder. You try with uh, you try with carry look adder. Okay. So in the combinational circuit level 1. Okay, this I already shared. This is AND gate using mux. Okay, AND gate using mux. How to design AND gate using AND gate using mux? We already seen in the digital now. Okay, we already seen in the digital. Is that default is I not okay. This is and mhm. Okay. First you need to write the, yeah, test bench. So you can design means you get design the AND gate using mux and OR gate using 2 cross 1 mux. Design all gates by using the mux. Okay. And next you have 4-bit adder subtractor. This is the circuit for 4-bit adder subtractor. Okay. Adder subtractor also we already seen. Okay. Mm. So adder subtractor, if you see this one, this code, if you see, first you need to write the code for the full adder circuit. Okay. Adder subtractor. One second. First here you need to write the code for. First you need to write the code for full adder circuit. Okay. And next what you need to do means here you see adder subtractor circuit. So how many full adders are you are using? 4 full adders you are using, no? So module full underscore adder, input A comma B comma C in, output sum comma C out, and assign sum equal to AX or BX or Cin, and assign Cout equal to AB plus BC plus AC and end module. First I wrote the code for full adder circuit. Okay. After that, so module, ripple carry, adder or subtractor. So there is a control pin. When control pin, that is M pin, when M equal to 0, this will act as a parallel adder. When M equal to 1, it will be act as parallel subtractor. Okay. So module, ripple underscore carry underscore subtractor. Input, how many inputs are there? 4 inputs are there. Input control and output 3 down to 0, S comma C out. And internal variables also I need to declare, while 3 down to 0 BC. Okay. So we already discussed the adder subtractor. No, A is directly given, but B is given through the XOR gate. Okay, B is given through the XOR gate. We know that suppose if it is XOR gate, I think I already explained the adder subtractor circuit. Okay, so adder subtractor circuit, you are suppose M pin is the control pin. Okay, so when M equal to 0, it is acting as what? Parallel adder. Parallel adder. Okay, and when M equal to 1, this is acting as what? Parallel subtractor. Parallel subtractor. Okay, so that means so you have, that means A you are directly giving to the full adder, but B you are giving through this M pin, through the XOR gate. Okay, so that is the B. A you directly giving to the full adder. So through the M pin you are giving through this XOR gate. So A XOR 0, what you are getting? A only, no? You know that A XOR B equal to what? A bar B plus AB bar. Okay, so A XOR 0 equal to what? A bar and 0 plus A and 1. Okay, so 0 plus A means you are getting A only. Okay, and next A XOR 1 equal to, you will get A bar. Okay, so here A XOR 1 means A bar and 1 plus A and 1 bar means 0. Okay, so here you are getting A bar. Okay, so how you are connecting means like two 4 full adders you are connecting, 4 full adders like this you are connecting. Okay, and next 4 full adders you are connecting, and so this line is there, no? This line directly you are giving. Okay, A naught, A1, A2 and A3, and B you are giving through the XOR gate. B you are giving through the XOR gate. This we already discussed for the offline candidates distance. Okay, so one input is B0, B1, B2 and B3, and one more pin is coming as the input from the control pin. Okay, that is M pin. Okay, and Cin also you are giving as a 1, means it will calculate the 2's complement. So we can subtract by using 2's complement method, no? So sum S0, S1, S2 and S3. Okay, intermediate things are there, no? This you need to consider as in the code, what we considered in the code. 1 second, this I am closing. In the code, we considered BC. Okay, BC is nothing but like BC0. This is BC0, BC1, BC2 and BC3. Okay, so like this you can design the, these all are full adder circuit. And next, what you are doing? So this is adder subtractor circuit. It can be act as parallel adder and parallel subtractor. And after that, assign BC of 0 equal to what? BC of, this is BC. BC means sorry, the input coming from this one. This one. This is BC0. BC0. This is BC0. Okay, not this one. So here you see. So That is, assign BC0 equal to what? BC0 under XR of control. Assign BC1 equal to B1 under XR control, and BC2 equal to B2 under XR control, and assign BC equal to BC3 XR control. Okay. I need to instantiate. How many times? 4 times. So full underscore adder. This is structural modeling. Okay. Full underscore adder equal to full adder 0, A0, BC0, control, S0, C out of 0. Okay. So 3 inputs and 2 outputs. Full underscore adder FA1 equal to A1, BC1, C out 0, S1, C out 1. And these are the outputs, and C out 0 is the input. It is acting as an input. And full adder 2 is A2, BC2, C out 1, S2 and C out 2. Okay. Full underscore adder FA3. FA3 is the instance name. A3, BC3, C out 2, S3, C out 2, 3. Okay. So this is my code end module. And coming to the test bench, this is my test bench. Okay. So like this, you can use if you see for ripple carry adder and carry lookup adder also. So you need to declare the test bench variables. So s comma c out as y data type, and four inputs are there, and a comma b as reg data type. Control also reg data type. I need to instantiate the design. No, ripple underscore carry underscore adder and adder subtractor dut instant. This is my dut name. Control s comma c out initial begin dollar monitor. So whatever any updated value is there, that will be executed. Okay. So control equal to 0 means what? It will do parallel addition. Control equal to 1 means it will do parallel subtraction. Okay. So 2 plus 4 means you are giving 6, 6 plus 3, 9, 9 plus 3, 11 you will get. Here 2 minus 1, 1, 9 minus 5, 4, 5 minus 3, like this you will get. Okay. So this one I will execute here. So add the source, add the design source. Next, create file. First, what is my file name? RCA Okay, not RCA. This is TB, no? This is my file name. What is my file name? This is my file name. Copy this and you paste. Select the location. Yeah, same thing I'm giving. Okay, finish. Okay, yes. So ripple carry as a subtractor is created. Open this file. Add a subtractor design file. Select all. Copy and paste here. Save this file. So ripple carry idea is created. Under this, 4 full adders are created. Why? Because I instantiated, no? I instantiated 4 times. So I wrote the code for full adder. Okay. After that, I am instantiating how many times? 4 times. Okay. So ripple carry idea is created. And next, uh, go to the simulation, add the simulation source, create the file. What is my TB? RCA TB. Okay. RCA TB. Okay. Okay. Finish. Okay. Yes. And next, RCA TB. So select all, copy and paste here. Save this file, and whatever the code you are seeing, the design source you need to set as top, and RCA TB also you need to make as set as top. So next, you need to elaborate the design. I need to see the design. Yeah, you got this. Our compiler converted this one into ripple carry adder, and one more control is there. When control equal to 0, so control is one more b input is coming from the control. Okay, coming from b output is coming from the b input and control through the XOR gate. When control equal to 0, XOR output means whatever the input is there, that same b input you are getting at the output, it will act as normal ripple carry adder. Okay, so when control equal to 1, you are getting the complement of b bar. Okay, complement of b. So complement of b means anyway carry in is 1 means it will calculate a minus b. So normally, like so negative numbers are represented in 2's complement and 1's complement, no? So how it will calculate means a minus b, you can write a plus minus b, again a plus. So in order to decrease the circuit complexity, I am using for the parallel subtractor, I am using the full adders only. So 2's complement of b, 2's complement of b. So what is this a plus 1's complement of b plus 1 plus 1. Carry in we given as 1, no? So that's why it will calculate the 2's complement of b. Okay, and next. So this is my elaborate design. I want to see the simulation. Close this elaborated design and run simulation. Run behavioral simulation. So see this. Expand this. Fit to page. Now you see here. Control equal to what? 0. Control equal to 0 means 1 plus 0. How much? 1 only. Okay. 1 second. 1 plus 0 is 1 only. Okay. 2 plus 4. 2 plus 4. 2 plus 4 means you are getting output sum equal to 6. Sum equal to 6. And next 6 plus 3. 6 plus 3 is 9. Okay. 6 plus 3 is sum here. You see here sum. Okay. So these are the like different values, 4-bit values, and 1 control equal to, now control becomes 1. No? 1 second. Control here 9, 6 plus 3. Okay. 6 plus 3 is 9 you are getting, and carry out is 6. Okay. 1 plus 0, 1 minus 0 is how much? 1. Okay, 1 minus 0 is 1, and 2 minus 1 is 1. Now it will do subtraction. B minus 9. B is 1 second. B is sorry, 9 minus 5. 9 minus 5 is how much? 4. 9 minus 5 is 4. 5 minus 3 is 2. Okay. So when control equal to 1, it will do parallel addition. When control equal to 1, it will do parallel subtraction. Okay. So this is about ripple carry and carry adder subtractor code. Is there any doubts or queries?